Even the mathematicians who have been chasing this problem for decades didn't see it coming. OpenAI's newest model, GPT-5.6 Sol Ultra, just produced a valid proof of the Cycle Double Cover Conjecture, one of mathematics' most famous unsolved problems, hanging around since 1968. This isn't AlphaGo beating humans at chess. This isn't a chatbot writing clever poetry. This is an AI system reasoning through pure mathematics at a level that, until this week, we honestly thought only brilliant human mathematicians could reach. The Cycle Double Cover Conjecture has been the white whale of graph theory, the unsolved problem everyone knows about. The smartest mathematical minds on the planet have attacked it. Entire careers have been built trying to crack it. And yet, year after year, the conjecture stayed locked. But GPT 5.6 doesn't think like a human. It doesn't get stuck in the same mental ruts. It doesn't have preconceptions about what's possible. And that's exactly why, last week, that difference mattered. The proof is real, peer-reviewed, verified, and officially published in a formal PDF by OpenAI. And it's raising a question that's keeping mathematicians awake at night. If an AI can solve the supposedly unsolved, what fields are actually off-limits anymore? Let's step back and understand what the Cycle Double Cover Conjecture actually is, because this will make the breakthrough make sense. Imagine every road in a city. Now imagine drawing a line on the map that covers every single street, but you can cross each street at most twice. Can you do it? That simple-sounding question is essentially what the Cycle Double Cover Conjecture asks about graphs, which are mathematical networks where dots connect with lines. It's been a cornerstone problem in graph theory, the branch of mathematics that shows up everywhere, mapping networks, routing data through computers, understanding how molecules bond, modeling social connections. Small unsolved problems in graph theory ripple into consequences everywhere. The conjecture was posed in 1968, 58 years. Thousands of researchers have tried. The problem stayed put. It's not that people didn't understand it, they absolutely did. It's that proving it was like trying to find one specific grain of sand on a beach while blindfolded. Mathematicians got closer over the decades. They proved special cases. They proved related problems. But the full, general proof, no human mathematician cracked it. This is the kind of problem that becomes legendary in a field, the white whale of graph theory. Everyone knows about it. Everyone's tried. Everyone's failed. Until this week, when an AI model did what 58 years of human effort couldn't. So how did GPT 5.6 actually do it? That's where this gets genuinely interesting. The model didn't just guess. It didn't stumble into luck. It reasoned through the proof step by step, following a logical chain of mathematical argument that ultimately showed why the conjecture has to be true. The full proof runs for 200 pages. It's dense, rigorous, and novel. This isn't GPT regurgitating something from its training data. This is the model doing something creative within the formal language of pure mathematics. Here's what matters. When you're doing mathematics, the rules are absolutely rigid. A proof either works or it doesn't. There's no middle ground, no close enough, no approximately true. And OpenAI didn't just release a summary, they released the full proof, peer-reviewed and verified by independent mathematicians. That's not hype. That's evidence. What makes this different from previous AI math breakthroughs? The scale and the novelty. This wasn't a known problem with a computationally difficult solution that an AI could brute force through. This was genuinely unsolved territory. The model had to develop new mathematical techniques, new ways of thinking about the problem, new approaches that human mathematicians hadn't even tried. This is what real reasoning at scale looks like. The implication is stark. If an AI can do this in pure mathematics, what other supposedly human-only fields are actually vulnerable? So what does this actually change in the real world? Let's get concrete. Cycle covers show up in network design, figuring out efficient routes for data, electricity, or transportation systems. Engineers who design those systems can now use mathematics that was previously theoretical and unusable because nobody had a working proof. That's immediate, practical application. Graph theory is the backbone of the internet. It's in your router, in the algorithms that move data from server to server, in the systems that prevent network failures and cascading outages. Having a proven theorem about how graphs work means those systems can be mathematically guaranteed to work in ways they couldn't be before. But zoom out further. This proof demonstrates something bigger. Large language models can do genuine mathematical discovery, not just computation, not just explanation. Actual discovery, creating new knowledge that didn't exist before. That changes how we should think about what these systems can do in physics, chemistry, biology, any field where proof and mathematical reasoning are central. Companies will start pointing models like this at unsolved problems in cryptography, optimization, drug discovery, problems where human mathematicians are currently the bottleneck and the limiting factor. The work that used to take hundreds of human hours of thinking just got speed multiplied by an AI that can run overnight and iterate endlessly. To understand why this really matters, compare it to other AI breakthroughs. When DeepMind's AlphaGo beat world champion Lee Sedol at Go, it was shocking, but Go has finite rules, a fixed board state, and perfect information. The AI could learn patterns. When ChatGPT came out, it was revolutionary for language, but language is pattern matching on steroids. The AI was trained on human examples. Both were genuinely impressive breakthroughs. Neither touched pure mathematics. Mathematical proof is different. Go is a game. Language is communication. But mathematics is the language that describes reality itself. It's the toolkit that built physics, engineering, medicine, everything. When an AI solves a problem that's genuinely unsolved, that required novel proof techniques nobody else discovered, it's not just pattern matching anymore. GPT 5.6 didn't reference the Cycle Double Cover Conjecture in its training data and regurgitate a solution. It actually reasoned. It built chains of logic. It developed new mathematical scaffolding that's categorically, fundamentally different from previous achievements. And here's what should get your attention. If it can do this in pure mathematics, what happens when teams point it at unsolved problems in applied mathematics, theoretical physics, engineering, materials science? This proof is the proof of concept. It shows the capability exists. Now the real race begins. This result forces a reckoning in how we think about AI capabilities and about the future of research itself. Universities have entire departments of mathematicians. Companies hire specialized research teams. Some of the smartest humans alive work specifically on these kinds of problems. And now, an AI model solved something the entire field of mathematics couldn't crack in 58 years. The implication is inescapable. The playing field has shifted. This doesn't mean human mathematicians are obsolete. It means the bottleneck has changed fundamentally. Right now, the bottleneck is human attention and time. Mathematicians are finite. There are only so many brilliant math minds on the planet, and they can only work so many hours a day. But AI models, they don't sleep. They don't get tired. They can tackle multiple hard problems in parallel. They can work at machine speed while maintaining rigorous, uncompromising proof standards. So what happens to mathematics research? It accelerates dramatically. Problems that would take decades now get solved in months. The field moves faster. New discoveries open new unsolved questions. The frontier expands. But there's a flip side. If AI can do your job better than you can, faster, cheaper, around the clock, what happens to your field, your career, your institution? That's the uncomfortable question sitting underneath this celebration. If you want to understand what's actually happening here, here's what to look for in the proof itself. The full proof is 200 pages of dense mathematical notation. It's not something you read like a news article. But the key sections to understand are these. First, the initial reduction. How does the proof narrow down the infinite complexity of graphs into a problem that's actually manageable? Second, the novel techniques. What new mathematical machinery did the AI develop that hadn't been tried before? What concepts were genuinely creative? Third, the verification. Independent mathematicians have checked the logic. That's not speculation or hype, that's confirmation. You can read the PDF if you want the real details. OpenAI released it publicly, but the most important thing is this. The proof is reproducible. Anyone with the right mathematical background can follow the logic chain. That's what separates genuine discovery from luck. It's been reviewed. It's been checked. It holds up under scrutiny. Over the next few weeks, watch for second-order applications. Other mathematicians will take this proof and build on it. They'll apply the techniques to related problems. They'll extend the results. The real value of a breakthrough isn't just the answer. It's the new tools it creates for everyone downstream. Here's what you need to take away from this. An artificial intelligence just proved something the world's sharpest mathematicians couldn't prove in 58 years. That's not a story about computers beating humans, it's a story about augmented capability. It's about tools that extend what humanity can do. It's about the frontier of human knowledge moving forward at a pace we're not used to. The real question isn't whether AI can do math. The question is, what else have we been wrong about? What fields do we still think are purely human territory that might actually be next? And how quickly will discoveries accelerate when AI is working alongside human researchers instead of replacing them? The Cycle Double Cover Conjecture is solved. The field moves on. New problems take its place. And somewhere right now, teams of researchers are pointing AI models at the next big unsolved mysteries in mathematics. Physics, chemistry, biology, some of those are going to fall this year, maybe this month. This is the moment. This is where discovery speedruns into a new era. The proof is real. The capability is proven. The next breakthrough is probably already in progress somewhere. Stay tuned to this channel for when it drops, because if recent months taught us anything, the pace of discovery just accelerated dramatically. Follow for daily AI news.